Oh, right. It needs to be a tuple. Right. We need to construct this tuple here first. We have this we have the subtract gets us the position, but we also need to give it comma current direction 1. Okay, so that adds one of the results. Then we just always add result.add current.p comma current.d plus 1. Int, oh, hang on. Right. Current p, current d plus 1, 1000. And current d minus 1, 1000. Actually, hang on. My life will be a little bit easier if we just say, yes. Direction, rotate. Yeah, rotate clockwise. Direction D goes to direction D plus 1 modulo 4. Oh, can it be applied? Okay, we cast that back to it. Yeah. Direction of int d plus 1 modulo 4. Oh, no, I did need those things. Okay, fine. Then rotate CCW d minus 1 modulo 4. Save. Run. Run all. All right, so now we can just say here, rotate clockwise current direction, rotate counterclockwise current direction. Okay, so these are the 3 positions that we could have gotten here from. All right. So now, for each um, for each position cost in from positions P. Am I grabbing that there? For declarative iteration variables for each bar position cost. Great. First question here is going to be, yeah, if best value seen of, or if best value seen dot what I want to know is, yeah, actually, no. Best value seen dot contains key position. Yes. If not best value seen contains key position, best value seen dot add position, and then right. I know. So int current, no, yeah, current value equals best value seen of p. So in fact, that actually should be right here. And that should be this kind of brackets. Okay. So we have the best value seen at our current position. So now, if the new position we're looking at doesn't have that, we're going to see best value at seen.add position current value plus cost. So now we've seen that's the best value we've seen for that position. And now we need to add to the position to evaluate, positions to evaluate dot NQ position, comma, current value plus cost. So this is going to enqueue that at as the new lowest thing. So we're always going to try to be looking at new positions based on the positions that we've seen that have the lowest cost to get to them, which should cause us to favor positions we can move to in a straight line. Okay. So now, and this is getting at, all right, not all code paths return a value, right. Return result. So now we don't need this. What we actually need to do is we need to say for each of these things, we're going to say best value seen dot add, and we're going to say positions to evaluate dot NQ NP0. Now, while positions to evaluate dot count is greater than 0, position P equals positions to evaluate dot DQ. Okay, and now we can do all this here. The current value is the best value we've seen for that. And then for every position and cost in from positions. So we might reevaluate a position if we see if we get there by a better route, and that's fine. But since it'll reevaluate each of its things here, right? So if the best value seen does not contain that key, then we're going to add that there, and we are definitely going to evaluate that position. Else, if best value seen for position is greater than current value plus cost, we have a new best way to get there. And so we're going to say best value seen for position equals current value plus cost. And we're going to say, we're going to reevaluate, or re-enqueue this for evaluating it. Okay. And that's it. For each of the positions that we might get there from, we enqueue that. While there's things to enqueue there. The other thing we just want to look at here is current value. We have a base case here. If current value is equal to, or no, not current value, sorry. If P is equal to start, return current value. And otherwise, we'll just return -1 because something's gone wrong. Build. Okay. Now, let's just see what happens if we say, oh, actually, we have one small problem. We check that that is a dot. I'm actually going to say, rather, does not equal a wall. That'll work a little bit better. Best possible score for find symbol map capital S. Find symbol map capital E. Does map exist? Hang on. What do we call it? Initial map. But that's not quite what we need because we have, that is going to be, right, and then we also need to pass in initial map. And we also need to set this thing, because this is not actually just one of those. It's a tuple of that and facing, and we always begin facing east. Which is right. Okay. Save everything. And I'm going to also do, I'm going to do the thing I've done in the past here. We're going to add in a quick, do I have just diagnostics? Good. Because we're going to step into this function here. Stopwatch timer equals stopwatch.start new. So while that's that, and timer.elapsed is less than timespan dot from minutes, or from, let's say, from seconds, 10. You're allowed to have 10 seconds to work. All right. Run all. Index outside the bounds of the array as we try to vector in direction D. Okay. Step of into D. Oh, hang on. D plus 4 minus 1. Try that again. Okay, 7036. That's correct. Okay, that just worked. Cool. Let's try it on the second map here. I do like it when the answer's right, coming right out of the gate there. Okay, run all. Scooch down. 11048. 11048. All right, let's run it on the real thing. $73, $432. Correct. Okay, part 2. Now that you know what the best paths look like, you can figure out the best spot to sit Every non-wall tile, so the start, dot, or end, is equipped with places to sit along the edges of the tile. While determining which of these tiles would be the best spot to sit depends on a whole bunch of factors: how comfortable the seats are, how far away the bathrooms are, whether there's a pillar blocking view, etc. The most important factor is whether the tile is on one of the best paths through the maze. If you sit somewhere else, you'd miss all the action. So you'll need to determine which tiles are part of any best path through the maze, including the S and E tiles. In the first example, there are 45 tiles, marked O, that are part of at least one of the various best paths through the maze. In the second example, there are 64. How many tiles are part of at least one of the best paths through the maze? Okay, the data we have grabbed along this way is actually pretty excellent, I think. So, okay. What I think I just want to do here is, okay, the best paths through the maze. You are a best, I mean, basically you are a best path as long as, I think, as long as the number for you keeps going down. Because every cell is kind of from how far you would get from the best path on the maze. So let's just do a quick thing here. All right, let's go back to partial data 1. Okay, and then back down to here. All right, so that's best possible score. Onward to part 2. Okay. So we've got all of this stuff, and I'm just going to go ahead and copy this. Okay, so this is going to should be a list of award for best path cells. Okay. So first thing I want to do here is this thing is going to calculate the best path. So right here, int compute best path, which is just going to do this stuff right here, because what I want to make sure we have is that this will also populate a bunch of the data structures, which we want to also be looking at here. So once we've done that, if compute best path is greater than 0, then everything is good. Oops. If compute best path is less than 0, return. Something's gone wrong. Actually, hang on, just throw new invalid operation exception. Something has gone wrong if the best path is less than 0. So now, at this point, we're here. We've found a best path, and actually what we do want here, though, is compute best path. Int best equals compute best path. Okay. So what we want to do now is just, I think we're going to basically, we know that the start and the end are along the best path. And I think the easiest way to do this is probably to follow the start. And for every position on the start, we want to look at the other positions to see, do we continue going down? And we don't need to worry about the turning here. So what we're just going to do now is again, this is a search algorithm. So I don't need positions to evaluate to be a priority queue anymore, and best value seen is now locked. So we're going to build ourselves a new queue. Queue System generic Q, right? Okay, yeah, Q coord. Yep. Q coord tiles to evaluate. And all we need to do is, and then we just need a list coord best tiles equals an empty list. Okay, tiles to evaluate equals, sorry, an empty queue. All right. Actually, it can be, all right, start position. Yep. Start.p is the first tile, or best tiles is start.p. Tiles to evaluate. All right. No, actually, oh, no, we can't do that. Okay. All right. Um, do I have neighbors in the coord set here? I don't, but that would be a really easy thing to do. Yep. INumerable coord neighbors of coord C goes to cardinal directions dot select CD goes to add CCD. Those are the neighbors. Great. So now for each tile in the neighbors of current coord, current equals start.p. Okay. For each tile in the neighbors of current, please rerun all. Thanks. Yep, I know that's invalid, but at least now you know about the other stuff you've got. The name neighbors does not exist in the current context. Oh. Run all, save, close, run all. Okay, now neighbors has been found. Okay, so for each tile in neighbors current, we're just going to do the thing. And again, since we have this buffer around the edge, we can just say if map at tile does not equal wall, actually, we can do neighbors.cur where tile goes to map at tile does not equal wall. Okay. We can now say, so these are all the tiles that actually exist. What we want to say here is int, we want to get the current value, which is again the best value seen here. Best value seen of cur. Honestly, let's just go with p. We'll start.p, p, p. Okay, so the current value is the best value seen at p. Now, what we just want to ask is if best possible score for oh right, there are 4 possible scores for that. So let's do a quick thing here because the best possible score is just no, because maybe you can go through. Okay. Actually, really, it's the. We care about the worst best possible score because that basically matters whether we're on a path. So, all right. All right, it's not best possible anyway. It's best value seen. Yeah. So, um, and what we want to do here is I want to do for each of our pause score in best possible score dot what is it? Or best value seen. That's worst best value in. Okay. And so pause will be count for the time. Entries. Dictionary does not contain a key for entries. Value seen dot. What do you call it? Elements? Not. I don't want the keys. I don't want the things. I don't want the keys. The value. There's a thing that should get me both. Is it items? C# dictionary iterator. Okay. For each key value pair. Okay. So I don't need to do anything in best value seen. For each of our pause score in. Okay, yep. There's pause, there's score. So there we are. All right. So for each of those, if worst best value seen, pause sub p. We don't care about the direction at this point. Equals math.max of worst best value seen pos.p or 0 and score. Display worst best value seen. I can't run that. No operator. Oh, canopy applied to operands of type int and int. Ugh. Let me take a quick look at C# dictionary here. Dictionary, D key, D value, right. I want to look at my methods. All right, contains key, right. Try get value. Right, when this message returns, contains the value associated. What I actually want is, can I get a get value or default? Or get alternate lookup? Nope. Okay, let's try get value. I just want, or no, maybe, right. If the key is found, otherwise is the default value for the type. That, right. Right. Because the indexer, if the indexer will be unhappy about that. Okay. And try get value has an out value there. So yeah, what we're going to just say here is int current value equals, actually no, int known value equals 0. Try worst best value seen dot try get value pos.p comma known value, which is an out parameter, then equals math